Hello everyone. So today I'm going to talk about serializable isolation and how CockroachDB supports serializable isolation. So let's first see what is isolation. So you must have heard about ACID in the context of database transactions. So I here refers to isolation, A being atomicity, C being consistency, and D being durability. So consider a critical user facing OLTP application. So you have multiple transactions happening concurrently. And what isolation means here is how multiple transactions can occur independently without any interference. Before understanding different isolation levels, let's go through what are the different transaction anomalies. So here are some of these: dirty write, dirty read, lost updates, non-repeatable read, phantom read, read skew, write skew. So these are some of the key ones. So I'll be going through some of these transactional anomalies and also showing a demo of one of the anomalies, right? And tell how serializable can avoid all these anomalies. Now let's look at non-repeatable read anomaly. Say transaction A begins at time T1 and at T2 you read a row R and you get some value. And then at time T3, other transaction begins, which is transaction B, and it updates the same row and same column, which is read by T2. Now at time T5, the transaction gets committed, and time T6, when you read the same row again in transaction A, you will get a different value. So you are reading the same row in the same transaction, but you are getting two different values there, right? So this anomaly is called as non-repeatable read. Now the next anomaly, phantom read. Consider a transaction A which starts at T1 and at T2, you're doing a select from the table where you're putting some condition. Say a particular column value falls between X and Y, and you get say three rows, row 1, row 2, and row 3. And at time T3, you are beginning a transaction B, and you're inserting a row into the table where you will have the column falling between the same range, X and Y, and you are committing it at time T5. And at time T6, if you are doing select again with the same condition, instead of seeing three rows, you are seeing four rows in the same transaction. So this is called as phantom read. Now consider lost updates. So in lost updates, say you are having a transaction A starting at T1. At T2, you are reading from the table with a condition. And then at T3, you are updating that particular row, say column is equal to column minus X. And then at T4, you are committing. Meanwhile, a transaction has started at T2, which is transaction B, and you are reading the same row with the same condition. And then at T4, you have updated that column is equal to column minus Y, and T5 it gets committed, right? In this case, so whatever update which has been done by transaction A is lost. This is called as lost updates. So now let us understand different isolation levels supported by various databases. So these are the key ones: read uncommitted, read committed, cursor stability, repeatable read, snapshot, serializable. This is in the order of weakest to strongest, serializable being the strongest. So by default, CockroachDB executes all the transactions at the strongest transaction isolation level, which is serializable, which permits no concurrency anomalies. It doesn't permit any of the concurrency anomalies which I have talked about. Now let us go through a quick demo of write skew transaction anomaly and how it is possible in Postgres with its default isolation level read committed versus how it is prevented in CockroachDB where the default isolation level is serializable. So what is write skew anomaly? So consider this table and say transaction T1 and T2 read the same set of rows, but transaction T1 updates row 1 and transaction T2 updates a disjoint row, which is row 3. But the updates might be dependent on the rows which they have read, and it can lead to a problem. Now let's jump on a demo. So these are the two tables I am using in my demo. Let's understand the use case. Say a hospital has an application for doctors to manage their on-call shifts. The hospital has a rule that at least one doctor must be on call at any given time. And in our scenario, two doctors are on call for a particular shift, and both of them try to request for a leave approximately at the same time, two concurrent transactions. Let's see how it works in Postgres with its default isolation level, which is read committed. Now I'm connected to the Postgres instance in two parallel terminal tabs. So I already created the tables, doctors, and schedules. Right? Now let's make sure at least one doctor is available across the week. Have this query, and you see for the entire week, at least one doctor is available. So after this, let's start the first transaction, right, where doctor one is applying for the leave. So I'll begin the transaction. And in this transaction, I make sure that at least one doctor is available for the specific day. So I execute this. Yeah, at least one doctor is available. I made sure that has happened. And in the other tab, parallelly, I'll start one more transaction where doctor 2 is applying for the leave at the same time. And I tested here whether at least one doctor is available for the same date again, right? So yeah, I see at least one doctor is available. I go to transaction 1, right, where doctor 1 is applying for a leave. So I am in the first tab now, and I'm applying for leave here, updating the on-call column as false, right? Update is done. And then I go to transaction 2 now, and again try to do the same thing because I have already read that at least one doctor is available as part of the transaction. And I try to confidently update on call as false for this doctor as well. And then I commit the first transaction here. It's committed. And then I commit the second transaction as well. It's committed. So now you can see that both the transactions have been committed. And then let's see schedule for that date, that particular date. Both doctors, the on-call is false. So now it has resulted in a state where no doctor is available on that day. Now let us see the same thing in CockroachDB, where the default isolation level is serialized. Now the same scenario, I'm connected to the same CockroachDB instance in two different tabs. So I have already created these two tables. I'm doing select star from doctors, and then I'm doing select star from schedules. It's all good. Now I'm going to start the transaction 1, where doctor 1 is applying for a leave, right? So I have beginning the transaction 1 and then seeing at least one doctor is available for a specific date. Yeah, it's available. So I'm going to begin the transaction 2 as well now, right? Where the second doctor is applying for the leave. And the second doctor also checks now here if at least one doctor is available. Yeah, it's all good. So at least one doctor is available here. So now I'm trying to update in the first transaction the leave on the first transaction where I'm setting on call as false, right? I've done it. And I try to do the same thing, the second transaction. Right? Now I'm going to commit this. And then I will try to commit this as well. So there is a transaction retry error here. It's because of CockroachDB's default isolation level, which is serializable. So under the hood, CockroachDB remembers that there was a read happened in transaction 1, which is a concurrent transaction on the same set of rows, which transaction T2 has read. And T1 might have tried to update a specific row based on that read. So now only way is to retry this transaction. And of course, because T1 has committed, when you read again, you will see that there is no other doctor on call and you can't update that particular row, right? And you have saved some lives. Thank you for your time, and let's meet next week with a new topic.